In the following set of videos, we're going to use the first derivative test to find the minimum and maximum value for different types of functions. So in this first set of videos, we're going to find the minimum and maximum values for polynomials. And we're going to find not just the relative min and max, but we're also going to find the absolute min and max, if they exist, over the entire domain of the function. Okay, so for any polynomial, the domain here is negative infinity to infinity. Okay, and the function polynomials are really nice. They have smooth behavior. It's differentiable everywhere. So if you remember, if there is a relative min or max, they're going to occur at the critical points. Okay, so the way you find relative min and max is you find the critical points of the function. So the critical points are where the derivative is either equal to 0 or the derivative is undefined. Okay, so for a polynomial, the derivative will always be defined, so we're going to find when the derivative is equal to 0. So what I'm going to do is I'm going to take the derivative here. So this would be 4x cubed minus 16x, and then the 16 will go away. So here's the derivative, and so what we do is we set the derivative equal to 0. And so at this point in calculus, you got to be really good at solving equations, because what you're doing is you're finding derivatives and then you're setting them equal to 0, and you got to find when the derivative is equal to 0, and that's solving an equation. And the main strategy that you use to solve equations is you bring everything to one side so that you can factor them out and set the factors equal to 0. And whenever you take the derivative and set it equal to 0, everything already is on one side. So the main strategy here is, can I factor this? And so in this case, I can factor out a 4x. And I'm left with x squared minus 4 is equal to 0. And now this is a difference of two squares, so I can factor that into a sum and difference of a binomial, like that. And so now I see that the critical points are when x is equal to 0, when x is equal to negative 2, or when x is equal to 2. So these are the places where the derivative is equal to 0. Okay, so if this has relative min or max, it's going to occur at one of those critical points. Now it doesn't mean that each of those critical points will be a relative min or max. So this is where the first derivative test comes into play. And we're going to do that by actually setting up a table, and it's going to, these critical points are going to break up the domain into these open intervals. So you'd have negative infinity to negative 2, negative 2 to 0. This is the first critical point. This is the second critical point. And then 0 to 2. And that would be this critical point, x equals 2, and this interval would be 2 to infinity. And so now what you got to do is you got to find out whether the derivative is positive or negative over each of these intervals. And since these are where the derivative is 0, then all I need to do here, if it's going to be either positive or negative over this entire interval, so I only need to check one point to see if it's positive or negative. And so you can pick a test point. Now something else you can do is this. This is a cubic, right? And it has a positive leading coefficient, so these are like the zeros of the cubic. And so a cubic with a positive leading coefficient is going to come down here, it's going to do its stuff in the middle, and it's going to leave here. So it means if these are the zeros, what it means is over here it's going to be positive, Okay, and then it goes through the axis, then it's going to be negative, and then it's going to be positive, and then it's going to be negative. So if you're good with that, and you can think about the derivative, or even graph the derivative and see when it's positive or negative, you can do that. But of course, if you graph the derivative to see when it's positive or negative, you could graph the derivative to see if or you can graph the original. You can just as easily graph the original function and see if the critical points are relative min or maxims, right? So what I'm going to do is I'm not going to rely on you knowing how that function is going to behave. So I'm going to show you how you can pick a test point. So this will be my test point, and then I'm going to plug that into the derivative. And when you plug that into here, into the derivative, you get negative, let's see here, I actually have it written down, negative 60 is what you get. And so this is negative here, the derivative is negative. So here, I got to pick a test point in this, so maybe I'll pick negative 1, and the derivative at negative 1 is 12. And so it's positive here, and so picking a test point here, I'll pick 1, and the derivative here at 1 is actually a negative 12, and so it's negative here, and then pick a test point of 3, and so then the derivative at 3 here is positive 60, so it's positive. So the first derivative test says if the derivative goes from negative to positive, it's a min. If it goes from positive to negative, it's a max. And then if it doesn't change signs, then it would be neither. So this is going from negative to positive. And so the way you think about this is if the derivative goes from negative to positive, then the function is decreasing where it's negative, and then at the critical point it's 0, and then it's increasing. And so you get a min at x equals negative 2. Okay, and then here it's going from positive to negative, so the function is increasing, it's 0, and then it's decreasing. And so here you get a max at x equals 0. And then here it's decreasing 0 and then increasing, and you get a minimum at x equals positive 2. So you get a min, a max, and a min. Now, what about the absolute min and max? Okay, well, for polynomials, well, first let me say, when we found the absolute min and maxes, we were finding them for continuous functions over a closed interval. And what we learned, and this was in the first section here, what we learned was that an absolute min and max is either going to occur at a critical point or at the endpoints of the interval. Okay? Now, here we do not have endpoints. This is not a closed interval, so we don't have endpoints to check. So what we need to know, this is what is happening on the interior here. These are all the relative min and maxes inside this open interval. Then I need to know what the end behavior is as you go to infinity and negative infinity. Now, for polynomials, this is pretty easy, because a fourth degree is going to be a polynomial that opens upward, kind of like a parabola, except it'll come down, do something in the middle, and then go back up. Okay, that is if the leading coefficient is positive. If the leading coefficient is negative, then it's like a parabola opening downward. It'll kind of come up, do something in the middle, go back down. Okay, and so this is a positive leading coefficient, and that means that this is like a parabola opening upward. So it means that there's going to be no absolute max, right? Because it goes off to infinity either direction. So we can say x equals -2 and 2 these are relative min. Okay, these are relative minimums, but see, this is a parabola. It's going to go down, do its stuff in the middle, and go back up. So these are also absolute minimum maximum as well. Not min. These are relative minimum, and they're absolute minimum. Okay, because the absolute min are either going to occur at a critical point or at the end behavior of this open interval. And the end behavior here, it's going off to positive infinity. So these have to be like relative min. And then x equals 0 is, these have to be relative min and absolute min. And then x equals 0 is a relative max. Okay, so we did all of this without using a calculator. And let's see how we did. So x to the 4th minus 8x squared plus 16. And so graphing here, looks like that. And my window it probably doesn't, it's -200 here. So let me go from -20 to 20. Might be better, give you a better idea. So the function looks like this, and those are the relative and absolute min and maxes. The relative and absolute minimums, and they occur at -2 and 2. This is a relative max, but not an absolute max, and it occurs at 0. So you see then how we can use the derivative to find these minimum and maximum values, along with this first derivative test, right? So let's try one more polynomial here. And so this is now a 5th degree polynomial. So it's an odd power, okay? So it has that 5th degree. And the leading coefficient is negative here. And so we're going to want to find the relative and absolute min and maxes over the entire domain, which is -infinity to infinity. And first, I just want to note that a 5th degree polynomial, so this has a negative leading coefficient. So it's kind of like a cubic equation that goes like this. Kind of comes down on the left. It comes down from positive infinity, flattens out, or it does its stuff in the middle, and then goes and leaves to -infinity. And so what this means is either direction is going from positive infinity to -infinity. And so there's no absolute min or max over the domain. If you pick just a closed interval, there would be an absolute min or max, but over the entire domain, there's no absolute min or max. Okay, so now what we want to do then is find the relative min or max. So we're going to find the critical points of the function. So the derivative here, bring the 3 down, we get 45x squared minus 5x to the 4th. Set the derivative equal to 0. And now we can factor out a 5x squared. And this is the difference of two squares, so I can factor that into the sum and difference of a binomial. Oh, and this would be 3 plus x, and then 3 minus x. A little weird having the constant and the x squared term switched around, but it's okay. And now this would be a critical point at x equals 0. This would be x equals -3. And this would be x is equal to 3. Now notice that this derivative is a fourth degree equation, but we only have 3 critical points. And the reason for this is that this is squared. So this critical point actually has a multiplicity of 2. Has a multiplicity of 2. And so there's really only those 3 critical points, even though this one technically has a multiplicity of 2. So on my table here, you'd have like negative infinity to negative 3. That would be at the critical point x equals negative 3. Then negative 3 to 0. And then 0 to 3. And then 3 to positive infinity. Okay, and so I'm just going to go ahead and put in some test points here. We'll do negative 4. And in here I'll do negative 1. Here I'll do 1, and then I'll do positive 4. And I've actually did these earlier. The derivative at negative 4 is negative 560. The derivative at negative 1 is 40. The derivative at positive 1 is also 40. And then the derivative at 4 is negative 560 again. Okay, now let me just make a point here. You want to be very careful, because when I did this originally, I took the test points and I plugged them back into this original function, and I did not plug them into the derivative. And I was able to go through and do the problem and find min and maxes, but it was not right. I got it wrong. So when I graphed the original function, I was confused. I was like, why didn't I get these right? What went wrong? And I had to go back and look, and then I finally figured out, I put these into the original function. I didn't put them into the derivative. That is important, okay, because the first derivative test, you're looking to see if the derivative is positive or negative, so that you can know if the original function is increasing or decreasing. So in this case, it's negative, positive, positive, so it's not changing signs there, and then negative. So here, your function is decreasing down to the critical point and then increasing. So you got a minimum at x equals negative 3. But here, it's the function is like increasing, goes to 0, and then increases again. So it's not switching signs, so it's not negative and decreasing. That would give it a min, but in this case it flattens out and goes back up. So this would be neither a min or a max. And then here you're increasing until you get to 0, and then you're decreasing. And so this would be a max, a relative max at x equals 3. Okay? And so let's go ahead and graph this and see if this is correct. And so let's see here. I'm going to put in 15x cubed minus x to the 5th. And I'm going to change my window. Well, first let me just graph it and show that this doesn't show the entire thing. One thing that you see is that you do see it is flattening out at 0. That's neither a min or a max. And it has this sort of behavior right here. Okay, but then these here, it's kind of hard to see. And in fact, these go way down. So this is where I had this y min was negative 200 and y max was positive 200 in order to see the behavior of the function. There you go. And then you can see there's the min, there's the max, and then at 0, it's neither. And then you can see that it doesn't have an absolute min or max over the entire domain because it's going off to infinity either direction. So that is the first derivative test for polynomials. And so in the next video we'll look at using the first derivative test for roots and fractional exponents.